Hey guys,
Hello.
seems like there are not many students in this meeting. So anyways, we will go ahead and continue anyways. So in this tutorial, we will be covering exercise 10.4, 11.1, 11.3, and 11.4. So there are some sub exercises which we will be skipping in this course. And I have mentioned them in the notes which exercises we will be skipping. So let me just go ahead and share my screen. Okay, let me know if you guys get my screen. Right, so are you guys able to see the screen?
Yep.
All right. Okay, so so this is the exercise 10.4. So we won't be doing 4.1, 4.2, and 4.6, which is introduction, paths and isomorphism. So our first question is question 7 from this exercise, and it is, what do the connective components of acquaintanceship graphs represent? So I'm assuming you guys already know what an acquaintanceship graph is. So here, so maximal sets of people with the property that for any two of them we can find a string of acquaintances that takes us from one to the other. So basically these connected components, so we find the string, or in other words, like an edge between two vertices which can take us from one to the other. Okay, so this is more like a theory question. The next question is, what do the strongly connected components of a telephone call graph represents? So the maximal set of phone number for which it is possible to find the directed paths between every two different numbers in the set. So strongly connected components represent the maximal set of phone numbers for which it is possible to find the directed path between every two different numbers in the set. So this exercise is mostly theoretical, and there is not such a computation problems in these exercises. And also because of the fact that we have skipped 4.1, 4.2, and 4.6, this becomes a rather smaller exercise. So this is gonna be mostly the theoretical questions from this exercise. Yeah, and let's move on to the next question. Yeah, and this is exercise 11.1. So in this exercise, we are skipping 1.2, which is tree as models. We won't be doing that. So the first question from this exercise is gonna be, okay. So in this one exercise, we are asked which of these graphs are trees. So here we'll take the first part. So part number A here. So if we look at this one, which of these graphs are trees? So if we look at this one, we have a way for part number A. We have the way for every node to reach the all other nodes, right? So therefore, this graph is a tree. Let's take, for example, C part here, B part, let's do that as a counter example. So for the B part, we see that if we have to make this graph in terms of a tree, then we won't be able to do so because there is no connection between this and this node. So therefore, we won't be able to represent this this sort of a graph in terms of a tree. So therefore, this graph is not a tree. And if we take a part number C, are you guys able to see the paint?
I see the word, not the paint.
Okay, that's what I'm trying to share, but I think I'm not getting that option here. Can you guys see the word now?
Can see the paint now.
Okay. All right. So we're just gonna stick with the Maybe what we can do is one more thing. Can you guys see both now?
Yeah, I can see both.
Okay, that's right. So for the part C, here, if we have to make a graph, make a tree for this graph part C, so it will be sort of like a hierarchical graph, like a straight tree. So where each node will be falling under the other one. So there is a way to basically represent this graph as a tree. So the graph can be represented as a tree. Let's take a last example, part E. If we take this graph here, part E, so we have a node, like a parent node, which will be this one, parent node, and then this can be the child nodes of that graph. So kind of just pull this on this node, so which will be like this gonna be the parent, and then it's gonna have 6 child nodes. So 1, 2, 3, 4, 5, 6 child nodes, right? So this graph can be represented as tree as well. Okay. Now moving onwards. So in this question, we are asked how many edges does a tree with 10,000 vertices have? So here the general rule is the number of vertices. So for example, if we take a look at this graph, so here we have 1, 2, 3, 4, 5, 6, 7 vertices. But if we look at the number of edges, we have 1, 2, 3, 4, 5, 6. So we have the number of edges E equals to n minus 1, where n is the number of nodes. So this is kind of a general rule for that. So here if we put E equals to 10,000 minus 1, then it's going to be E equals to 9999. Okay. Okay. Any questions? Okay, so this is also a very smaller exercise. And let's move on to the next exercise. It's gonna be 11.3, and we won't be doing the traversal algorithms here in this exercise. So which kind of cut down a lot of content from this exercise as well. So in this exercise, we will be we have to construct a universal.
Sir, for 11.3, I think we're only covering 11.3.3. That's what it says on Moodle.
I'm sorry?
For 11.3, it only says we're covering 11.3.3.
Let me just be double sure. Yeah. So here we will be only covering only 11.3.3. Yeah, you're right. So here, so in this exercise, so we will be covering the traversal algorithms only. So which is the infix, prefix, and the postfix representations. So let's take this question, the first one here. So in this exercise, we have to construct the universal address system for the given ordered rooted tree. Then use this to order its very vertices using the lexicographic order for their labels. I think this question will not be including that. Let me just get some question from that exercise. So when is your final exam scheduled for?
17th of
17th of April, this month, right?
yeah, Monday.
Okay, very close. This leaves us with the last tutorial for this course. All right. Okay, so this is going to be our first question for this exercise. So part number 7, question number 7 here. So we have to determine the order in which a pre-ordered traversal visits the vertices of the given ordered rooted tree. So here we have to figure out the order using the pre-order cursor. So I can just write it here. So here in the pre-order, we will be visiting node A first, and then we will be visiting node B. Then we will be visiting node D. Then we have E. Then we have F. Then we have G. Then lastly, we will have C. Okay. Any questions here? Okay, let's take a little challenging one. Maybe the 9th one. So here we will be visiting A first, and then we will be visiting B. Then we will be visiting E. E. Then we visit K. Oh, sorry, M. K. K. Then we visit L. Then we visit M. Then we visit F. Then G. Just gonna write it down the line below. The next node visited is N. The next one is R. Then S. We have C, D, H, we have O, we have I, we have J, we have P, and lastly, we will be having Q. So it's a kind of a lot of nodes here, but the important is we first will visit the root A, and then we're trying to go all the way to the left, and we visit the right. Okay, so A, B, E, K, L, M, F, F, G, N, R, S, C, D, H, O, I, J, P, Q.
So wait, we don't count the C and the 9 after that, or no?
Sorry, which one?
The C.
The C is after S.
Oh, okay. Never mind.
Yeah, this one.
Okay.
Okay, so this one here. The next question will be question number 17. So we have the expression x plus xy plus x divided by y, and there is another expression, so we have to represent this expression using the prefix notation, postfix, and the infix notation. So first of all, let's only take one. So for example, we can take this one, or either this one. So let's maybe take this one. So when we take this one, and let's try to draw the graph here. So the binary graph for this one will look like, so plus, because of this plus, it's here, there is this plus, and then there is this plus because of this, and then there is a division, and then this x comes here. Now this one here is a multiplication. So I will just put on multiplication sign. This is not x, this is multiplication. And then we have this xy here. X and y. Now for this one, we will have the division. We have x and y. We have this x, and then we have this y here. Okay, so we have the binary representation of this x plus xy plus x divided by y. Now let's try to create the prefix notation for the binary tree. So in the prefix, so what we will do is we will have plus this plus and then this plus, and then we will have x, and then we will have the multiply sign. This one here is multiply. Let me just be more obvious. This one is multiply. So multiply, then we have x, then we have y, then we have the division sign x and y, and this is for part B. Part A is here. Part A. Likewise, we will create the postfix annotation, which will be x, y, multiply plus x, y divided by plus. Okay, so it's gonna be x, y multiply. So x, y multiply plus x, y divide plus. Part number D, the infix notation. It's gonna be x plus x times y plus x divided by y. Can put it in a bracket. Questions? Okay, if no questions, let's move on to the next question. It's going to be the 31st question. So we have here, show that any well-formed formula in prefix notation over a set of symbols and a set of binary operators contains exactly one more symbol than the number of operators. Okay, so we have, we can prove this statement using the mathematical induction. So let's do that. So prove by mathematical induction. So again, just like every time, we will assume some function and then we will write what it represents. Let S X represent the number of symbols and number of operators in the well-formed formula X perspective. Now, this statement is true for well-formed formula of length 1. We already know because they have one symbol and 0 operators. Now assume the statement is true for all well-formed formula of length less than n. A well-formed formula of length n must be of the form multiply x y, where multiply is an operator and x and y are well-formed formula of length less than n. Then by inductive hypothesis, we will have S times xy, which is equals to S times x plus S times y, which is equals to 0 and x plus 1 plus O of y plus 1, which is equals to O of x plus O of y plus 2, which is equals to because here O of times xy equals to 1 plus O of x plus O of y, it follows that s multiply xy equals to O multiply xy plus 1. Okay, hence proved by mathematical induction. So this was a kind of long proof. Let me just summarize what I did. So here, what we were trying to show was that a well-formed formula in prefix notation over a set of symbols and a set of binary operators contains exactly one more symbol than the number of operators. So just like any other proof that we have done before for mathematical induction, we assume some of the functions which represent something helpful to represent in the function in the proof. So we have s of x and o of x as well, which represents the number of symbols. The s of x, it represents number of symbols in the well-formed formula x, and this one here represents the number of operators in the well-formed formula x. Now, when in the basis step, when the statement is the formula is of length 1, then when it's of length 1, then the number of symbols and there will be 1, and then the number of operators and there is 0. And we know that 0 is less than 1, which means that here operators is 1 less than the number of symbols. So this basis steps is proved. Now moving on to the inductive step, what we do is we assume the statement is true for all well-formed formula of length which are less than n. And then we say that a well-formed formula of length n must be of the form xy, where this times is an operator and xy are well-formed formula of length less than n. By inductive hypothesis, so we have the symbol, the number and the symbols in this formula xy times, which is an infix notation of that formula, so which is equals to s of x plus s of y, and then we apply the definition that the number of symbols in the formula x is exactly one more than the number of operators in that formula. Now, resolving that equation, we get this, and then at the end, we figured out that in this one here, in that formula, the number of symbols is one more than the number of operators. So therefore, it proves mathematical induction. Any questions here? Okay, if no question, let's move on to the next exercise. So we have 11.4, and exercise has everything except the 11.4.1, which is the introduction. Okay, so we have to, let's take the part number 3 here. So we have to find a spanning tree for the graph shown by removing edges in a simple circuit. Okay, let's do it here. So we're going to be doing this graph here. So here we have to represent this using a simple circuit. A spanning tree for the graph shown by removing the edges in simple circuit. Okay, so we have this tree here. We have the nodes A. This is node A. This is node B. This is node C. This is node D. This is gonna be E, F, and G. Okay, A, so A, okay. So now in order to represent this with spanning tree, so it will be, so because this one A, it can be reached through B, C, D. We don't need this root, so we'll cancel that out. So A, and then in order to reach C, I need this root here, and then I can reach D from here. Now I need to reach E, which will be this one here. Now I will need F here. Here I won't need this one because I can get to F using here. I won't need this one either. So we don't need the BFH. We don't need the BEH. And we don't need the B and G edge here because I can reach all the nodes from here. Okay, let's take another question. So we have to, question number 19. So describe the trees produced by BFS and BFS of the wheel graph starting at the vertex of degree n, where n is an integer with n greater than or equal to 3. So with BFS, the initial vertex is the middle is the middle vertex, and the n spots are added to the tree as this vertex is processed. Thus, the resulting tree is K with DFS. We start at the vertex in the middle of the wheel and visit a neighbor. One of the vertices on the rim. From there, we move to an adjacent vertex on the rim, and so on all the way around until we have reached every vertex. Thus, the resulting spanning tree is a path of length n. Okay, so in the BFS tree, what we're doing is we are traversing the 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 breadth of that search tree first before we go into the depth of that tree. But in the DFS, we are doing the some other logic. So there we are basically going in the depth of that tree first before we actually traverse through the breadth of that tree. Okay, let's take another question. Okay. Okay, now suppose that an airline must reduce its flight schedule to save money. If its original routes are as illustrated here, which flights can be discontinued to retain service between all pair of cities where it may be necessary to combine flights to fly from? So basically, it is something that we have done already, which was over here when we were creating the spanning tree, right? We were basically cutting down the unnecessary routes. Now, this is another example. So we're cutting down the routes that we don't want because the airline is trying to save some money. Okay, so now the answer is a possible set of flights to discontinued are, for example, from Boston. Boston to New York, so we can cancel out this flight until we'll be able to reach it through some other destination. We can cancel the Detroit versus Boston. Okay. Boston and Washington. Cancel out that. We can cancel out Washington. We can cancel out New York and Washington. The other possibility is to cancel out New York and Chicago. There is Atlanta. To Washington, we can cancel out that. Atlanta to Dallas, we can cancel out that. So we can cancel out Atlanta, Dallas, Atlanta to Los Angeles, we can cancel out Atlanta to Los Angeles. We can cancel out Atlanta to St. Louis, Denver. Cancel out Dallas to San Diego. Cancel out Dallas to Los Angeles. We cancel out San Francisco to Seattle. So these are an example of some of the flights that can be canceled out, and still there will be a way to reach that destination through some other city. So there are different possibilities in this sort of a graph, because there are many destinations and the airline is operating in way too many cities. So they can save money by cutting out some of the flights from these destinations. Okay, this one marks the end for this tutorial as well. I believe this is the last tutorial. So if you guys have any questions, any feedback, anything, feel free to okay, all right, nothing. Okay, all right. Well, I wish you good luck, guys, and yeah, work hard and prepare hard for the exam. Wish you good luck. All right, bye, guys.
Goodbye, man.
Goodbye.